Let's look at this one. Lisa, I think this is going to be problem 7 in your homework. Lisa is planning an event. She needs to rent tables that will seat at least 60 people. There are 5 round tables, 16 rectangular tables available to rent. A round table seats 6 people, while a rectangular table seats 10 people. If the rental cost is $16 for each round table and $40 for each rectangle table, how many of each type of table should she rent to minimize the rental cost? So we have some event planning to do, and there's only a limited amount of tables, and we have a certain amount of people we're trying to have room for. Theoretically, it's the same as the previous problem, but the conditions have changed. So what are we trying to solve for? It says how many of each type of table should she rent to minimize the rental cost? So somewhere down the line, I need to minimize rental cost. Minimize rental cost is my goal here. Okay. That's pretty common. And usually you're either trying to maximize profit, minimize cost, minimize time, that kind of thing. Maximize protein. That's what we're always trying to do. Okay, so how much does each thing cost? It's $16 for a round table. It's $40 for a rectangle table. If you're okay with it, I'm going to let round be X and rectangle be Y. It doesn't matter, but I just need to call them letters. And both of those words start with R, so I don't want them to be R1 and R2. That's too confusing. So I think X and Y would be a choice we could make. If the rental cost is $16 for the round and $40 for the rectangle, we could make an objective function of 16x plus 40y, and we want to minimize this. Somehow we're going to minimize that. We need space for at least 60 people, and there's only a certain amount of each table. A round table seats 6 people, so maybe I'll do seats. So a round table is 6 people. A rectangle table is 10 people. And we need at least 60 people. So which way does that inequality go? I need at least 60 people. So 61 would be fine. 62 would be fine. But 59 is not fine. I need at least 60 people. So 60 is the minimum. There's only a certain amount of tables. There's 5 round tables. There's 16 rectangle tables. Okay. So we have boundaries on those too. So for my X, there's only 5 available. So the amount I order has to be less than or equal to 5. There's only 16 available rectangle tables. So it has to be less than that. We have our objective function, so that looks good. And then I also claim, doesn't say, but I claim that they have to be at least positive. They could be 0, but they can't be negative. It can't be a negative amount of round tables. That's not going to work. So we have to be in the first quadrant, otherwise it doesn't work at all. Okay. All right, so that's the setup. Now, how are we going to do it? So I think what we need to do to solve this problem is we probably should graph it. If we could find the corner points of the feasible set, then somewhere one of those corner points must be the minimum, okay? One of them might be the maximum, but it wants the minimum. So the small setting. So I think we're gonna have to graph it to find those corner points. How are you gonna do that? Well, you have a line x equals 5, y equals 16. Those are fairly easy to know where those are. That's just a horizontal and vertical line. But we also need to know where does, what are the intercepts of this? So you have 6x, 60. So it seems like x equals 10 comes up, and you have y equals 6. Is it clear where I'm getting those x and y intercepts? Is that clear how I'm finding those? So I'm just saying if 6x equals 60, x must equal 10. If 10y equals 60, y must equal 6. So that gives me my x and y intercepts. And now I've got some things I can graph and try to find where this thing lies. All right, so from that, let's see if we can figure it out. We know we have x equals 5, x equals 10 we need to graph, and we have y equals 6 and y equals 16 we need to graph, and we need to be in the first quadrant. And the only thing I'm doing with the graph is I'm just finding the corner points. That's the only purpose of the graph, is to find where the corner points are. Right? If you just guessed because of the context of it being math class, I mean, a lot of times it's just the intersection between the two things, but here we don't really have those two lines, so we have to kind of assume it's something else. So let's see if I can't graph it. Now, graphing it by hand is kind of risky because it's not as precise. Let's say that that's x equals 5. And let's say that this, if I double that distance, this would be 10. Yeah. And then we want y equals 6, so it should be roughly about the same distance as before, but just a little bit more. And then 16 should be about that, and a little bit more. I'm going to say that's 16. Pretty rough stuff there, but just trying to get an idea of where these corner points might lie. So I have 10 and 6. Y equals 16. Now let's check and see where everything is lying. Where are they pointing to? So y is less than 16 says you got to go down. X is less than 5 says you need to go to the left. To the left. The 6 and 10 says you need to go away from 0. This one says you need to go this way. All kinds of arrows. And it has to be greater than or equal to for y, greater than or equal to for 0 x. So I think we're in this spot. There's a corner point. There's a corner point. There's a corner point. There's a corner point. So I think that's my region. I think that's where we are, and those are the corner points. And the theorem says that the minimum will lie on one of those corner points. The minimum of the objective function is what I'm looking for, not the smallest point. I'm just looking for where is the minimum of this function. Okay, which means I'm going to have to test them. Okay, so what are my points? Some of them are really easy to know. Like for instance, that's 0, 16, so that's pretty easy to find. And then this one is 5 and 16. That's pretty easy to see. It's not bad. This one's 0 and 6. That's not bad. The only one that's kind of annoying is that one where x equals 5 and it intersects with this other line here. So I have x equals 5 and then I have, so I'm thinking about this right here. I know x equals 5 at that point because that's that vertical line, but I have the other line I have to deal with. So I'm going to have to solve for what the y coordinate is for that. All right, so x equals 5, so 6 times 5 is 30, plus 10y equals 60, 10y equals 30, y equals 3. Okay, I think that's 5 and 3 there. Are there any questions about how I just found that corner point? So let's try to find the minimum. The way we'll do that is we'll plug these in. So that'd be 0 plus 40 times 16. That would be 16 times 5 plus 40 times 16. That would be 0 plus 40 times 6. And this would be 16 times 5 plus 40 times 3. I want the one that's the smallest in this particular problem. 40 times 16 is 640. 16 times 5 plus 40 times 16 is 720. 40 times 6 is 240. 16 times 5 plus 40 times 3 is 200. Again, we want, what is the small one? What's the smallest in this problem? We want to minimize cost. So there's the minimum, and that occurred at 5, 3. So minimum location, that's where it was located. So to the best of my knowledge, a lot of this, I mean, the way I hear it, and I can't believe it's true, but a lot of this was redeveloped in the 50s and 60s, which seems so recent to me since we're just graphing things on X and Y. But not everything needs to be developed until it needs to be developed. So it was kind of sitting there waiting for someone to tackle the problem. But and then of course in those problems it's more than 2 variables. But the way I read it, it had something to do with shipment, and I mean I think it started with like cargo ships. And how do you do that in general? So here we're only doing 2 variables, but to my understanding, uh, if you want to do 100 variables, 200 variables, you need a pretty robust system to do it for you, and you can't graph it. So how do you do it? Well, from my research, it sounded like even up until the 70s, they were coming up with new ways to do it. And I think there were programming languages that were written just to solve problems, harder problems than this, but those types of problems, to tackle that. Which is interesting. I didn't know that until a few years ago, actually. Uh, so that's kind of interesting to me. It just seems so recent, for something that you never know. You never know. Sometimes things seem like an easy problem. Um, you know, like I say, if you go into three variables, automatically, the difficulty has quadrupled. So it's quite surprising that that would be the case. Okay. All right. So